Picture a real service checking a user's role, tagging a log line, comparing a header value. All day long, the same literal text like admin gets typed over and over, maybe thousands of times. If Java created a brand new object for every single one of those, you'd be burning memory on duplicate copies of identical text for no reason at all. That's the problem the string constant pool solves. It's a flyweight. Instead of a new object per use, everyone shares one. 3 completely unrelated variables can all point at the exact same object sitting on the pool's shelf. Here's the payoff. User role, REQ role, and log tag 3 different variables, in 3 different parts of your code all end up pointing at the exact same admin object. Not 3 copies. 1 object, 3 references. And this only works because string is immutable. Once created, its characters can never change. If strings were mutable, sharing one object across 1,000 callers would be a disaster. One edit would silently corrupt everyone else's copy. Immutability is what makes this kind of aggressive sharing completely safe. Here's a detail that trips up even senior engineers. For years, every memory tuning guide said the string pool lived in permgen, a separate, deliberately capped region that also held class metadata. That was true, through Java 6. And it created a nasty failure mode, in turn a lot of unique runtime strings, and you could blow through permgen's fixed cap and crash with an out-of-memory error even with plenty of regular heap free. It looked like a leak. It usually wasn't. Then Java 7 moved the string pool out of permgen and into the regular heaps old generation right alongside your normal long-lived objects, garbage collected exactly the same way. Java 8 finished the job, permgen was removed entirely, replaced by metaspace. But metaspace isn't a rebranded permgen, it only holds class metadata now, lives in native memory, and auto-resizes instead of hitting a hard cap. So if someone tells you to check permgen on a modern JVM, that's outdated advice. There is no permgen to check. 2 lines that look nearly identical can behave completely differently, and the decision is made exactly once by the compiler. Write a literal, and javac resolves it into the pool at class load time. Here's the surprising part, even JA plus VA pools, because both sides are literals, the compiler folds them into the single constant Java before your program ever runs, as if you'd typed it directly. That's compile time constant folding, and it's why 2 lines that look like concatenation can behave exactly like a literal. Now change one thing, make one side of that concatenation a variable instead of a literal. The compiler can't predict a variable's value in advance, so it can't fold this at compile time, it has to build the result fresh, at runtime. That's exactly what newString does too, an explicit instruction to allocate a brand new object on the heap, bypassing the pool entirely. Same visible text, completely different object, and that gap between looks the same and is the same object is where the classic string bugs live. This is the single most common string bug in Java, and it always starts the same way, a check like user role == admin that passes every test, then silently fails for one customer in production. == never compares text, it compares identity. It accidentally works when both sides are pooled literals, and quietly breaks the moment one side is built at runtime. Intern is the fix, it checks the pool for equal content, either registering your string as the canonical entry or handing back the existing one. Either way, you end up holding a real pool reference. So here's the one habit that prevents this entire class of bug. == compares identity object to object, not text to text. It's only reliable when you're certain both sides are guaranteed pooled literals, and in real code, you're rarely that certain. == compares actual content, character by character. It doesn't care where the string came from, pool, heap, concatenation, deserialization, it's correct every single time. If you remember exactly one thing from this whole video, make it this: compare strings with == always. Let's watch it happen, live. String a equals the literal Java that resolves into the pool. String B equals the same literal Java same pool entry, no new object gets created. So a double equals B, true. Not just equal text the literal same object in memory. This is the case that lulls people into trusting double equals for strings in the first place, because most of the time, in most code, both sides really do turn out to be pooled literals until they don't. Now the twist. String C equals new string of Java. The new keyword forces a brand new heap object, completely bypassing the pool even though the text inside is identical. So a double equals C, false. Same characters, different objects. This is the exact shape of bug that ships to production, code that only ever saw pooled literals in testing, meeting a runtime built string for the first time in front of a real customer. But C dot equals A, true because equals reads the actual characters, and doesn't care how C was built. Let's connect this to shapes you'll actually see. 1. A service that ooms every 3 weeks like clockwork that's almost always unbounded interning of high cardinality data, like user IDs, where every value is unique and the pool just keeps growing. 2. Heap usage drops after a JDK 8 to 17 migration, with nobody touching the code. That's not a bug, newer JVMs just reclaim pooled entries more efficiently. 3. A feature flag check passes every test, then flickers for one customer. Look for a double equals comparing a config value against a hard-coded literal. 4. You're deduplicating 40 million rows a day across 200 categories. Interning is exactly right here, since a couple hundred pool entries do all the work. 5. Someone needs a real memory number for a capacity audit. Remember, the pool's cost is per unique value, not per reference, so 1,000 variables sharing one string cost one string's worth of memory. And that's the whole series in one line. Literals share automatically, new and runtime concatenation opt out, and when in doubt always reach for dot equals, never double equals.